Okay, thank you all for joining into my talk. Now, unfortunately, I only have 12 minutes, so I'm gonna go very fast, and I also need to skip some parts. So if you have any questions, you can always contact me later. What I want you to take from this talk is the motivation to study more and also to use different kinds of metrics. And that is apart from the Hamming metric, maybe also apart from the rank metric. So in this talk, we're going to focus on the Lie metric. And in order to introduce it to crypto, we're going to look at some information set decoding algorithms. So this is joint work with all these amazing people. And let's get straight to the motivation of why we want to change the metric. So as you all know, because you're in this conference, McAleese originally proposed this crypto system using GOPA codes, and they suffer from large key sizes. So many researchers have tried to fix this issue by exchanging the family of codes. And very famous is the example of Niederreiter that proposed to use GRS codes. And the reason behind this is GRS codes can correct more errors, and as a thumb rule, the more errors you can correct, the harder is the problem. But as we all know, they're vulnerable to algebraic attacks. So it seems, at least to me, that we were always trying to find some balance between security and key sizes. But then I had hope again with the NIST standardization process, because the crypto systems that were achieving the lowest key sizes are based on the rank metric. So let us look at why the rank metric can achieve lower key sizes. So I hope you all know the definition of the rank metric for matrices, and let's get straight to the definition of the rank metric for vectors over an extension field. So VR over FQ to the M, and now your rank weight of your vector is the dimension of the FQ vector space that is spanned by its entries. What you get then are the FQ to the M linear rank metric codes. And we usually focus on those because they're also FQ linear rank metric codes. Just choose your favorite basis of FQM over FQ and extend your vector to become a matrix. Now the difference to the Hamming metric is very clear. Already the support is different. In the Hamming metric, the support are the indices of your non-zero entries. And in the rank, it's the FQ vector space spanned by the entries. So the Hamming weight is the size of the support, and the rank weight is the dimension of the support. If you want to solve the syndrome decoding problem over the Hamming metric with brute force, what you're going to do is you're looking for an error vector of length n and the size of support t. So you're doing the Newton binomial and choose t. Whereas in the rank metric, you are over FQ to the m, and you're looking for an FQ vector space of dimension t. So that is the Gaussian binomial, which is much bigger. So by changing the metric, you made the problem, I want to say harder, but what I mean is the algorithm becomes more costly. Of course, I can also point out a different reason why the rank metric has lower key sizes. And that is the Hamming metric ISD algorithms have been studied very thoroughly. Since 1962, when Prange proposed his first ISD algorithm, and there have been many improvements in the last 10 years. The first algorithm that solves the rank metric SDP problem was proposed in 1996, and only very recently there came out a new benchmark where they applied the min rank problem. So this confirms what I'm trying to say here. The rank metric needs a lot more studying. But in general, it seems like a good idea to change the metric for code-based crypto. So let us look at the Lie metric. You can define the Lie metric over integer residue ring step mod m. Now pick your representative between 0 and m minus 1, and then the Lie weight is defined to be the minimum of x and m minus x. I put here the example of ZAP mod 8, but I usually think of it as this triangle. Even though it's not a straight line, it should be these points. Okay, now if you change the representatives from minus m minus 1 half to m half, what you get is the L1 norm. That is a very strong connection the Lie metric has to the L1 norm that we also use to prove that the Lie syndrome decoding problem is NP complete. But that's for another talk. Of course, when you're looking at vectors, then your Lie weight is defined as the sum of the Lie weight of the entries. And what should be clear too is that the Lie weight of a vector is always bigger than the Hamming weight of the vector, or equal. And this stays true for codes. The minimum Lie distance of a code is always bigger than the Hamming minimum distance. That means we can correct more errors, and there is the whole idea. Now, the decoding should be harder and we should get better key sizes. So when I say Lie metric code, what I mean is an additive subgroup of Z mod m to the n. And now, because we are over finite rings and not finite fields, we don't even have a dimension. What we can put as a parameter for our code is the type, that is the cardinality of the code. Together with Anna-Lena, we focused on quaternary codes. So we are over Z mod 4. And why we did that is because it has a very strong connection to the classical coding theory with the Hamming metric. And that is through the gray isometry. So you are over Z4 with the Lie weight, and you go to F2 to the 2 with the Hamming weight. And of course, you can extend this to vectors if you do so component-wise. And that means most of the theory and most of the codes are known over Z4. And if we're going to find a code that has all the properties that we want, it's going to be over Z4. Or so we thought. So the differences to classical coding theory is very clear. Our systematic form is not as nice as over finite fields. We have, this is the generator matrix, and below is the parity check matrix. The type of this code is 4 to the k1 times 2 to the k2, and you can see this k2 very clearly in the generator matrix because we have k2 of these rows that are all multiples of 2, and so they're not invertible and you can't get rid of them. I'm going to skip the part of ISD in the Hamming metric. I'm just going to assume that you know that. Important is that we have given a parity check matrix and the syndrome, and you're looking for an error vector that has a given weight. And now what you're going to do is you're going to assume some weight distribution on it. The important thing about ISD algorithms is anyway its cost. And the cost is given by what does one iteration cost times how many times do we have to do such an iteration. And that is the reciprocal of the success probability of one iteration. And this is completely given by the weight distribution you have assumed on your error vector. For example, in Pranja, we assume that outside of the information set, so in n minus k positions, you have weight t. And so that's your success probability. Now, to translate ISD algorithms from the Hamming metric to the Lie metric is not the difficult part. You just have a systematic form that looks a little different, but you can still assume a weight distribution like in Pranja, that here in the information set there are no errors. You get something you can multiply out, and you get a condition that you can verify. The difficult part is that techniques that are fast over the Hamming metric don't have to be fast also over the Lie metric. Now I put here Pranja just because it's fast to show, but it's not really using any speed up that I can show here. The only thing I can put is we get a new success probability. So outside of the information set in n minus k1 minus k2, we want Lie weight t. And there are this many vectors that have that. And the 2 here comes straight from the gray isometry. Now assume that the CBCrypto system, you can use it as you know it, but with Lie metric codes. Unfortunately, we didn't find any code that has all the properties that we want, not even over Z4, but we still want to compare it to the Hamming metric and say that was a good idea. So what we do is we fix a security level that we want to achieve, and now we're going to find parameters that achieve the GV bound, because then we know there exists such a code. So here you see the GV bound over the binary in the Hamming metric, and this is the GV bound over the quaternary in the Lie metric. And if you do that, you get the following table of theoretical parameters. Now the first thing you should observe is that in the Lie metric, we get much better key sizes. The second thing you should observe is that we would like to have a small k1 because then our key sizes is pretty small. But when we programmed some random quaternary code, what we could see is that with high probability we have a small k2 that is only a few non-invertible elements. But nevertheless, the key size is still about half of what we have in the Hamming metric. And to put both of the cases makes the table also complete. We know the key size should be somewhere between here for this fixed security level. But important disclaimer, these are only theoretical parameters. We are not actually proposing a code that has such K1 or K2 as parameters. And so they should really be treated only as theoretical parameters. And the table should just tell us the Lie metric has its advantages and we should study them more. Now, how about generalizing these ISD algorithms to Galois rings of the form Z mod P to the S? Well, your systematic forms get messier and messier. Of course, for the purpose of ISD, you could just assume a simpler systematic form like this, where we put all the non-invertible elements here into one big matrix D. Now, you could say that I'm cheating because we are not taking care of the special structure that we are given, but this simplified version might already be enough to do exactly that. And for that, we have to look at Lie because unfortunately in Pranger we cannot see it. So in Lie we assume that in the information set in this E1 here, we have Lie weight V and outside T minus V. If you multiply it out together with this simplified systematic form, we get the following two conditions. And now look at the second condition, forget about the P. What you see is again a syndrome decoding problem, but now we are over a smaller ring, that is Z mod P to the S minus 1, and our matrix D is of smaller size. So what we did is solving it iteratively with this simplified systematic form. Now, being an iterative algorithm, the computation of the cause is very difficult, and so I put it as one of the open problems. And also when we got back the reviews of the article, there was a very interesting question. Right now we have translated techniques that we know from the Hamming metric to the Lie metric. How about we translate techniques from the Euclidean metric to the Lie metric? Would that be any faster? That's a good question. And as I said before, a very big open problem is we still want to find codes that have the properties that we want in code-based crypto. And what we are working on right now are identification schemes and signature schemes in the Lie metric. And thank you very much for your attention.
Thanks, Violetta.